think I just turned.
Hi, I'm Felix from Imperial College London in the biomechatronics lab. And I'm going to talk about my work designing a new compliant bioinspired knee joint. So we want to investigate the specific structure of the human knee to see which features can be replicated or to benefit walking robots and prosthetics. And our main method of doing this is by building a physical model of the human knee that mimics lots of the internal structure of the human knee. So there are two key areas we're going to look at improving. They're increasing high load performance, because we know that current powered prostheses often lack this. And we also want to know whether we can replicate some of the sensing ability of the human knee using similar methods. So why are we doing this? From a mechanical point of view, we know that the high load tasks require largest moments, mostly in the center of motion. For example, stair climb at about 60 degrees, sit to stand at about 80 degrees. And we know that also in humans and from cadaver studies that the largest moment arms are present in that same region. And outside of that region, small moment arms are actually beneficial because they reduce the total distance the actuator might have to move, or the muscle in humans, and will reduce excessive torque at the extremes of motion, so there'll be a reduced risk of damage at the point of hyperextension. And then from a sensing point of view, we know that the human knee has mechanoreceptors in the soft tissues and in the ligaments, and that these are used in neuromuscular control of the joint. So we want to investigate whether a similar type of sensing can be used in a mechanical knee to estimate joint position or user intent or forces acting on the joint. So this is what we've developed sort of so far. It has, that was the pointer thing, yeah. It has two smooth condyles that slide and roll over each other as the joint rotates. Springs represent ligaments and have a similar stiffness to the springs in the human knee. And there are sensors that we can put in here in parallel with the ligaments to measure how much they've stretched at any given time, so that we can get continuous measurements of that. And the condyle shape and the ligament attachment points and the stiffness, so they're all taken from the literature, from cadaver studies and from other sort of bone scans and that sort of thing. And the joint is designed to be powered using antagonistic muscles, so it's exactly the same, or in a similar way to the human joint. We've sort of summarized the quadriceps and the hamstring muscle groups down to just one muscle each to simplify the system. And we've represented the patella in this version as a bracket, just to sort of simplify the design in this iteration. The location of the attachment points of all of these tendons changes the moment arm of the joint. So we've selected those so that the moment arm of this joint matches, or as closely as possible, matches that of a human knee. And this is the result of that optimization. So here we have the moment arm profile using, this is just in a sort of kinematic simulation of the joint. This is what the moment arm profile of our joint should look like. And the human knee profile is underneath, although in the literature there's quite a lot of variation, especially at this end. Some of the curves come up and then sort of stay up quite high. So we weren't too bothered that there was that sort of difference. And if we look at a constant moment arm joint, and if we have a constant moment arm joint with the same total actuator length requirement that you'd need for the full 120 degrees of motion as our joint, we find that for something like a stair climb, you need a smaller actuator volume for like a hydraulic actuator, because the maximum moment arm is only concentrated at those bits where you really need it in the middle, and at the extremes of motion where you don't need so much of the moment arm. You can get away with less movement of the actuator, essentially. And you can see that the results are quite similar to the human knee. And so we've tested this with an optically tracked system just to check our sort of model was right. And we've got in the squatting rig. So we've got it to do some squats, and the fit is roughly right. In fact, it seems to fit the human moment arm even rather better at the end there. So just to quickly conclude, we've designed and built a joint with a moment arm mechanism that's similar to the human knee. We've started to look at using the sensors in the ligaments for estimating joint position, and we've done some initial work on a previous version of that joint, but really that's the thing we're starting to look at more now to work out what can really be done there. And thanks to my sponsors who paid for me to be here, etc.
Hey, do you hear me? Okay. Actually, so I was wondering about the kinematics of the knee, because the human kinematics is not a revolute joint. Basically, if you just like fold your knee, you will see that your foot is slightly away from the support foot. So my question is, do you take this into account in your design?
So in we've got like a simple kinematic model that we use to design the joint, but the idea is that having designed it, it will now perform in that same way as the human knee. So it'll move because the profiles of the condyles are the same, and the stiffness of the ligaments and the positions of the ligaments are the same, it will move in the same way to the human knee when you do those sort of movements, yeah.
Thank you.
Quick question about the condyles themselves. So what governed the choice of articular surface geometry that you chose for the two contacting surfaces?
So the femoral one we just took from a bone scan, just taking like a sagittal plane of a femur.
I see. Okay.
And then the tibial one is basically generated so that the ligaments can be, once you know the ligament attachment points and their lengths,
Right.
there's only like one valid tibia shape that will like.
Okay.
So does that make sense?
Yeah.
So the kinematics of knee literature, to my understanding, sort of like a while ago was like, hey, let's measure the kinematics of a knee in a cadaver. And then people realized, well, actually the kinematics of the knee depend upon what muscles are active and when they're active and so on. And so do you have a good sense about, it seems like in your device, it will also depend upon the forces, right? Like, and do you have a sense about the sort of the range of kinematics you can get depending upon the forces that are exerted, and how you might help understand human knee function from that?
So exactly that problem is part of the motivation for, I guess, why we're doing this, because lots of those measurements around joint function are done without taking into account muscle loads. So the idea is that now we have this model that we hope is relatively accurate. We can then use that to do these investigations using more muscle heads as going forward. Does that sort of answer your question?
Okay, one last question.
Okay. Hi. Yeah, my question is, if in your experiments you're basically doing extension and flexion, why did you model the ACL instead of the MCL and the LCL?
Because our model is basically only in the plane. So the shape of the condyle, the profile of the condyles is sort of constant in the out of plane direction. So for this model, we sort of said the LCL and the MCL help to reduce those sort of twistings out of plane, and those are the motions that for this version we're neglecting. So we neglected those sort of restraining features, and also just to keep it like simple and do it sort of one step at a time. And we thought that the ACL and the PCL were more important in this model, because in this movement in the plane.
Okay.
Cool.
And our final speaker before the videos is Siavash Reza Zadeh.